Hello, welcome. And for this course, we will introduce a little bit about ADCME, a junior library for automatic differentiation, and for incorporating neural networks into complex numerical solvers. And ADCME library is for automatic differentiation in scientific computing, and it aims at general and scalable inverse problems in scientific computing with gradient-based optimization techniques. And TensorFlow is the backend for ADCME automatic differentiation library. And why TensorFlow? And here is a comparison of different AD systems. We have PyTorch here. Also, PyTorch is the blue line, and also we have TensorFlow graph mode and the purple line, and I also have Template. Template is the fastest among all, except the manually craft icon. And yeah, Template is actually a source-to-source conversion. It's more like the hand-coded automatic, not automatic differentiation. It's like a hand-coded differentiation system. But it's automatic because it is converted automatically by computer programs. And also you have the Python eager mode, and yeah, it actually has the worst performance. So that's why we use the static graph mode in ADCME, and you can see the graph mode performs quite well, and it even outperforms the hand-coded programs for high. This is out of the box, but this is the size of the problem for large problems. And we also have Junior, and actually ADCME is a junior library. Its interface is in Junior, but in Junior actually people already have an AD system, the so-called Zygote. But we are not using that for scientific computing. It looks like it's in an early stage. And also we have Deep Sharp, and the performance is here. So that justifies our choice for TensorFlow static graph mode, and that's what is used in ADCME. So how does ADCME works? ADCME is not yet a lattice wrapper for TensorFlow in Junior. It provides some core computational functionalities that is missing in TensorFlow. For example, in TensorFlow, they have sparse linear algebra library, but mostly that's for deep learning utilities and for like computer vision and natural language processing. They are not designed for scientific computing. For scientific computing, you may want a lot of sparse servers, and you want sparse indexing and also sparse slicing, and you want that to be high efficient, because that's what is commonly used in scientific computing. And you also need a lot of other libraries for doing scientific computing. For example, the finite element library that is compatible with this framework, and also finite volume library, and also a lot of library that is missing in TensorFlow, because TensorFlow is eventually designed for machine learning tasks instead of scientific computing tasks. And also the choice, also ADCME is built, has interface in Junior. That is because in Junior, if you write a function natively in Junior, and that's numerically computed in Junior, and then that the code is compiled directly into using LLVM, which is highly efficient compared to Python for scientific computing. In Python, you just do not want code the basic linear algebra or something similar in scientific computing. For example, treating the boundary conditions or many other things. You cannot easily use NumPy to do that. So you have a lot of costs because you are using Python. But in Junior, you do not have this problem. If you want to carry out a numerical computation, just do that in Junior. You will get the best performance, and the performance usually outperforming many other languages. And that is why we want to interface in Junior, but you also want to have access to the TensorFlow automatic differentiation utilities. So this is the architecture for ADCME. It's built on TensorFlow, but more than TensorFlow, it has a sparse linear algebra library and also has custom optimizers. Well, yeah, maybe you have already used that in your research, like RP-opt or NL-opt, which is very popular optimizers in scientific computing. And also you want some other utilities, and for example, you want a file element or something.